Today we are going to do section 6.5, but before that I want to scan the answers again. Okay, this is the same answer we've been doing for a while, but here's the, let's see, this particular chapter, and I want to scan the next page before I forget. And here's the answer page for the following page. Right, let's see. Okay. All right, so there it is, and then zoom in a little closer. Okay, and the bottom. All right, so that actually, I think I'll zoom in the top. Why do I need to zoom in the top? I don't know. Maybe a little on this side. Yeah, keep it straighter. That should be good enough. All right, next let's scan page 195, which we have already done, but I'll do it again just quickly, especially this part. Okay, that should do it. Next, page 196 and 7. Let's see, I'll put it in the middle, straight up. Okay, that should be okay. And then a little closer on top and on the bottom. That should do it. Next, page 198 and 199. Let's see. Okay, a little closer on top. And on the bottom. All right, and I think that's it. So let's start with section 6.5. First, there's a quick introductory paragraph. Please read that yourself. Okay, and what we're going to do in this section is simply shifting coordinates. That is, we used to integrate with respect to in one direction. We're going to integrate it in another direction. That sort of thing. We are and now at the bottom of this page. I mean, as in section subsection 5.1. Let's look at this. Where this is just the homework we did in the previous section, where we proved that the integral, you can switch, basically exchange the dy dx, okay? We used to integrate from a to b of dx and then a to x of dy. Now we integrate from a to b of dy and then some other thing of dx. Now to do this, as we did in the homework, what we did is that and when we work out the details of the integration region, we realize that it's some kind of a triangle. And that is the same thing we're going to do right now. So please look at example A. Okay, we're integrating from a to x and then 0 to x. And the goal is to flip it around so that we integrate y first. So, and to do that, what is the region that goes from, x goes from a to b, okay, and y goes from 0 to x. So if you draw that out, very soon then you realize is this thing right here. X goes from a to b and y goes from 0 to y equal to x. So it's this trapezoid region here. To switch the order of integration, what you're going to end up having to do is cut this trapezoid into two parts, the rectangle and the triangle, and then work out the details, okay, which I have done right here. Now, let's see, what are we talking about? Example A? Yeah, I think so. That is, right. So anyway, please do example A yourself, okay? It's just a matter of staring at all the endpoints and making sure the order is correct. And once you've done that, the answer will come out. So next, so please do that. In fact, pause the video and do it right now, okay? And let's get this over with. It's more tedious than difficult. So anyway, next, let's look at example B, the same kind of story. And example B is some kind of a different region, okay, and something like this. So if you have to switch it, then you have to cut it in half in order to do dy first instead of dx. And so again, please pause your video and do this right now until you work it out in your head. And here are the details if you have any questions. It's kind of a mess here, but if you look at it long enough, it all makes sense. And eventually the book wants you to calculate the area of this thing in both ways to make sure that as a checkpoint, that is, if your integration endpoints are correct, then you should, calculating the area should come out with the exact answer of the area of this triangle here. So that's example B. And so next, so please pause your video and do example B, okay? And until you're done, and I'm gonna, while I move on to example C. Example C, the same kind of deal, except there's a catch here, okay? If you look at the integration of example C, the integration looks fine and normal, right? Except that you notice that at this point, the limit of the integration changed. That is, what was on top is now on the bottom. And as a result, this part of the area is going to be negative by the time this integration come out. So if you change switch the order of integration, you will have to count this part as negative, which is what it shows here, see? But that's not all. You also have to cut this thing in half. Did I draw it as cut? No, but you get the idea, okay? So besides that point, the rest is very straightforward and extremely tedious. And so please, again, pause your video and do this yourself. Here's what I did in case you have any questions. I told you it's tedious, okay? You end up having to do this, cut it into four parts. Cut it right along the middle where in the horizontal line where it intersects, and so you have 4 triangles to work on. And it's a lot of work just to integrate that silly little thing, but that's what the book wants us to do, so please do this, okay, right now by pausing the video. And again, this is what I did. Just make sure all the details come out. Check all the details of which end goes where, okay? And then so that you turn your x into an integration with respect to y, and that is that. So next, I'm going to move on to section 5.2 on this page, bottom of this page, polar coordinates, where we're going to just do the shifting again, except this time we're going to use polar coordinates. All right, and okay, how are we going to do that? Well, to do the shifting, first we'll go back to this formula on the previous page right here, except that we're going to change all x's into r and all y's into theta, okay? Now, if you do that change, the formula still holds because the formula doesn't care, okay, what kind of variable you're using. It's just a definite, it's just some integral, right? So, and if all the variables are called dummies. That's what the book says right here, see? It is a dummy. X and y are dummy variables. Okay, so it doesn't matter if we change x to r and y to theta. And so if you do that, then you have the formula. You basically directly have the formula of integration, switching the integration order of integration in polar coordinates. And to prove that makes sense, I have it written right here. That is, the polar coordinates, when we do the shift, is the integration of some function, right? Doesn't matter what function it is, which is the same. And then we have an r dr here. I have 2r down here and up here. That way you have an, because the ds is in theorem 3 is r dr, is r dr. I have yeah, I have the theta written here. Why do I have theta here? It should say, this should say d theta. Did I get the order wrong? Dr. Yeah, I think it's correct. Whatever. The point is we need to do the shift. So I stick another r here, which cancels out with this, just so that this matches with the ds from theorem 3. Yeah. Maybe I should show you theorem 3 first. theorem 3 is a couple pages ago. Where was theorem 3 again? It doesn't say here. Well, whatever. We'll just find theorem 3, page 192. Did I say that? No? Whatever. So theorem 3 is right here, where we have the integral of f theta r ds is the same as f theta r, that is, ds is the same as r dr. That's why we have that extra r dividing on the bottom, as seen here. So being that this equation is equal to that, and that is the region are the same, so that is going to be equal to this, and as a result, both integrals, whether we turn the order of integration or not, is going to be equal to the double integral. Yeah. So that is that's that. That explains. I just want to explain why this thing here has an r on the bottom. Okay, and so to fit theorem 3, and as a result, then in the polar coordinates, you can shift the order of r and theta based on the Dirichlet's formula in the previous page. Now I have a graph drawn here. Okay, now please look at this. Spend some time, pause this video right here, and spend some time looking at this thing until it makes sense to you. That is, in this the example, I have of demonstrating the example D. I have r equals to theta. That's the black curve there, which is also called theta equals to r. Where originally we have our theta, which goes from well, maybe that's original, I don't know. Our theta goes from A to theta goes to B, and then the functions are theta to B. Okay, if you switch it to r, then you have to look at it as r equals to A. That's the, whoa, why did it do that? Oh, it dimmed out. Okay, and then now at this point then, r equals to A, and that is for r equals to A, and then r equals to B. And then your theta as a function of r is equal to, it start at A, that is this line, and goes to theta equal to r, because the definition is over here, okay? Theta equals to 5r is part of the definition. So please stare at this for a while until this whole thing makes sense to you. Or draw yourself if you're in the mood, okay? And so that is example D. Next, let's look at example E on page 197. We are going to invert the order of integration of this integral theta from 0 to pi over 2. That's fine. And r goes from 0 to whatever that is, right? And what is that? If you were to plot that into the Desmos calculator, or if you think about it for a few moments, then you quickly realize that this thing, r equals to 1 over cosine theta plus sine theta, is just x plus y equal to 1. You just let x equal to r cosine theta, and so on. You quickly come up from this equation to that equation. Okay, and so that is just some regular triangle. Yeah, the world's most boring triangle, basically, intersects at 1, and maybe not boring, but standard, the world's most standard triangle. And so then our theta is described very simply as 0 to pi over 2, and then that's the angle, okay? And then the r will go from 0 to that line in terms of theta happens to be that thing, r equals to that theta, okay? So that's r of theta. Now we have to switch it to r of r, and that is not so easy. The best way to do it then is, well, the only way to do it basically is we're going to cut it into 3 parts. Right, as the book shows. Now, please work this out yourself, okay? All of it, and this is I don't know. This is the only interesting part of this homework problem. So what happens is the only way we can get this to switch is integrate over 3 regions. There's R1, R2, and R3. All right. So I have it drawn right here. Now so to integrate this I have 3 regions, okay? That is, the first region is this is R1. I write R1 as R1 prime, and I like that better. Anyway, so R1 prime is the round, the quarter circle region. That's the easy part, okay? And R2 prime and R3 prime is more difficult to figure out. But what we need to do is first we need to figure out what theta is in terms of R. It ends up being this thing for this part. And then up there, from this point on, is a different value. It's a slightly different equation because of the definition of arc sine. That is inverse sine. And the reason for that, let me, well, if you plot it, please work that out, okay? There's a bit of a detail there that we need to not take it lightly. And to come up with that formula, what you do is you use the sum of angle, sine sum of angle formula, and that comes out fairly quickly. But being the sine inverse only covers a small area. To cover the rest of it, you have to do this part of the equation. That is, sine of pi over x. Sine of pi minus x is the same as sine of x. That's the formula I use here. But anyway, so with that, yeah, you can finally come up with the 2 formulas that represent, all we're doing here is represent the straight line, okay? So this part of the line in polar coordinates use this formula, and then from this point on to the end, it has used a slightly different formula, all because of arc sine's domain restrictions, that sort of thing. Anyway, so please work out those details yourself. Now, once we have that, then we got to figure out, that is, this is the R formula. Please bear this carefully in mind, okay? Because working with R theta and R, very soon you get them confused. Like, which one's theta and what am I doing now? Was it R or theta? It gets quite confusing. So keep this formula right here. Refer to it anytime you try to remember what am I doing. Okay, so now with that, you'll be able to figure out that RR is that's the second one. It goes from, angle goes from pi 1 over this line, which is, and where's the second one? Okay, let's see, R goes from, that's 1, the radius goes from 1 over 2 to 1, and then the angle goes from 0 to this line as a function. Theta of R is this particular function. And anyway, so please, well, it takes, anyway, so please go through this yourself, okay? It will make sense once you stare at it long enough. Or better yet, don't even look at what I'm doing until you work this out yourself, okay? Without looking at this. This is just the answer. And once you worked it out, then all this will make perfect nice sense. And yeah, it's just a bunch of details, and that somebody better figure this out, kind of a thing. So and that somebody is you. And so that is the end of this section. Now for homework, before I forget, I want to mention this particular formula right here. All right, see, look at this formula. This formula is not related to what we have on this page. This is a formula you're going to need in your homework, so that's why I wrote it here. The formula states, at least I think it is it? I don't know. But anyway, the formula is either this section or next section homework, okay? The formula states that if you have integrating something, okay, gx, hy, that is a function that can be completely factored into a function of x only and a function of y only. If that is the case, and integrating over a rectangular area, a, b, and c, d, then you can just split them into two integrals, like this, okay? And this is in the book Calculus 3 if you want to look it up. I just want to remind you of this because you're going to need it in the homework. And so with that, let's look at what homework we're going to do. For homework, on page 197, please do problems, let's see, let me write it down first. So for homework, please do problems 1, 5, 6, 7, 11, 13, and 14. Okay, that should do it. And when you're done, we'll talk about them. So for homework, let's look at problem 1. I don't think there's much worth mentioning in problem 1. You just follow the definition, which is on page 182, and that gets to the answer. Now, and that's problem 1. Problem 5, similarly, I don't think there is much going on there. Yeah, okay. So that is that's problem 5. And then next, problem 6. And let me check something. Yeah, I think there isn't much worth saying about problem 5. I'll just, let's see, why is my camera not focusing? There it is. Okay, so problem 5 is that. Next, let's look at problem 6, which is on the other page. Okay, problem 6 is, again, I think there is not a whole lot worth mentioning. I did plot the graph for it to show you, okay? The only difficult point is not to confuse r with r theta. So here's problem 6, where I should draw r as in little bits. See, from r as the r increases, as you can see, it spans the entire semicircle. Okay, from the little bit, okay, and then it gets bigger, and the radius gets longer, and the radius eventually get to the other side. So that is how I can confirm that my answer is correct, as the book doesn't show the answer for this problem. All right, so that is problem 6. And next, problem 7 is let's see, yeah, problem 7, again, there is, I don't think there's much to say about that. I just did it in one line, but I also, yeah, okay, so let's look at the graph for it. I also graphed this thing just to make sure. Let's see, let's look at the graph is fairly simple, right? So it's just a simple little thing, and there's not much catch to it. And so once you see that, then you can go, the radius can go from the small circle to the big circle, and then theta, the formula of the theta is, actually I think it has to be cut in 2, right? Which I have the cut line right there. So once you cut it in 2, then the RR should come out okay. And so next. Now problem 11 is similar to that example in the book where the limit of operation crossed. I mean there's a crossing happening here. So as a result, when you switch the order of integration, then you have to cut this thing, and also bear in mind that the thing over here has to be negative. Okay, so once you remember that, then everything should be okay. And I have the whole thing drawn here, and bear in mind the definition. Okay, and what in this case we're doing r theta. We've been doing so much r of r that you might have forgotten how to do r theta. So we have to go back to doing r theta with this definition firmly in mind. And then let's see, yeah, the r is and you have to figure out these formulas, right? And then the original line is r equals cosecant, and that's the horizontal line. R equals the secant is the vertical line. It just works out that way. And then these, then you have to calculate that this is equal to, what is that? That is r equals the arc secant 4. I'm talking about the line here. But why would that be? Let me think. Okay, I went and fixed it. See, now it says theta, much better, isn't it? Let me make this a little bit bigger. All right, so see, now it says theta, which is far superior. And so we have this thing, and to calculate this r theta, I'll make it a little. So bear in mind this formula, then we have to calculate all 4 regions. See, I've shaded 4 different colors. And so you calculate the r theta from all 4 regions. Theta goes from this line, theta equals r cosecant, and then to and for the blue area, okay, it goes from this dotted line to the middle line, y equal to x, or theta equal to pi over 4, and then goes from pi over 4 to theta equals arcsecant for the pink region, and so on. There are a bunch of details. Please stare at this until it makes sense. I also have it written down right here, all the details. Okay, that is let's see, yeah, problem 11 right down here. We have all the stuff. There's a, well, not that much. It just goes from here to here, and that's about it. You just have to figure out all 4 things. So you end up with 2 things, and the big areas are added, and you have to subtract the small areas because they are inverted, which means the integrals are negative. So next, let's get out of staring at domain areas, okay, which we have done plenty of, and let's look at something more interesting. That is, we're going to prove some kind of integral being equal, okay? And how are we going to do that? Well, here the book provides us with a convenient hint. We're going to plug this into the Dirichlet's formula in the previous page, and then add them up. All right, so that's what I did here. We have problem 13. We have to prove that these 2 things are, prove this is equal to that. So to do that, first I will let gxy equals to f of x times f of y for convenience. And then remember, if this is the case, then gxy is the same as gyx, okay, because due to the way it's defined. Then in that case, then this formula right here, then we'll plug it into the Dirichlet's formula, I believe, which is AB and XB, okay, which turns into AB and then AY, and then and changing dy and dx and stuff. And so that would be equal to, let's see, actually I should look at it first before I talk about it. All right, now continuing, I'm getting myself confused with this. Now, the formula we have goes from AB to XB. And that AB to, so here it is, AB to XB, right? And we will rewrite it as in this form, where g of xy equals to f of x times fy. Did I say that? Yeah, I said that somewhere over there, which is fine. And then next, this equation equals to this one by the Dirichlet formula. That is, you can integrate from one variable x to from a to y. Okay, is the same as from x to b, basically. And the Dirichlet formula has the variables exchanged. Let's see, let me find it. Where did it go? The Dirichlet formula is at right here. Okay, the Dirichlet's formula goes from a to x and then y to b. All right, there's no difference. We can go from a to y and then x to b. Same thing, which is what I have here. We have applying the Dirichlet formula with exchanging variables x and y, we have x goes from a to y, and then y then goes from x to b. And let me show you that again. The formula says from a to x and then y to b. Okay, this is the original formula going down from a to x and then y to b. The one I just exchanged variables, it goes from a to y and then x to b, but it's the same thing. See, these 2 formulas are the same, or should I say these 2 formulas are the same. Now this formula is also the same as this one right here, where it is. Let me think about this. So at this point, I exchanged variables again. Anyway, so here, instead of what is y here, I call it x. Okay, otherwise it's the same thing. So the integral is the same, and then we have two integrals. As a result of that, you notice that this one integrates from a to x, and that one integrates from x to b. which means it's this whole rectangle. So this is the first part of the triangle is 1, and the second triangle is 2. Okay, for the integration. So as a result, 1 plus 2 is equal to the whole thing. That is integrating from A to B both directions. And this is, we can do this because gxy and gyx are the same thing. Now please stare at this a little bit until, because it's slightly confusing, or very confusing, because I keep changing x and y. But once you look through it, then everything should come out okay. So once you figure that out, then 1 plus 2 is equal to this integral. And then the integral, when the integrand can be separated by factoring, then as I mentioned earlier, right at the end of the lecture, that is the same as each integral individually multiplied together, which is this. And that's the end of problem 13. Now problem 14, then we have to prove a whole bunch of stuff. So I'm just going to do the case when n equals to 3 and n equals to 4, because we already did n equals to 2, which is problem 13. Now what we're going to do, let's try n equal to 3, okay? So then we have 3 variables, right? And then what we're going to do is that we write it out, and then we'll hold the x right here as some kind of a constant. That is, we're going to deal with just this part of the integration. Now by problem, so by problem 13 then, we have, that equals a double of, see, problem 13 basically says, where did problem 13 go? Okay, problem 13 basically says that we start out with 2 of this kind of variable, AB and XB. That will be equal to AB and AB. Okay, 2 of them add up to be this thing, is what problem 13 did. So we apply that theorem. So then we have if we have holding x as the constant for now, then the integral of from xb and then yb is the same as the integral from xb and xb, and 2 of them is the same as the integral from xb to xb. And then the next step we're going to do is actually integrate that thing. Okay, what is the integral of from x to b? Then performing the integration, then we get, if we let big F is the antiderivative of small f, then we calculate that thing, it equals to something like this. And something like this is exactly this integration, right? This integral is exactly this integral. And so we have a 1/3 here, and there's a 2 here, and then so that's where that n factorial comes in. So the n factorial will be 6 when you move the 3 over here. And so that's why it works for n equal to 3. And next, n equal to 4, the same thing. We have we'll hold the x constant, and then apply what we just did. Okay, so then so that is equal to 3 times that thing right here, which by the time we worked it out, that would be equal to 1/4. So then, because the 2 parts end up being here. Okay, and then so then once you do the integration in the exact same way as this, okay, so you notice that when we do that, then the power of this integral has increased to 4. So each time we do this, we divide by 4 here, which will end up being multiplied on the side. So that's why in general this formula as given in the book works, where n factorial times this stuff is equal to these integrals to the power n. And that is that's the end of problem 14. You should officially probably write this out more of a mathematical induction way, right? That to say that how in general this will work out. I didn't do that because I don't want to bother. So please do that yourself if you're interested. Okay, write it out as formally as you can, and explain why as n increases the same pattern holds. And yeah. And that should be the end of this section.